the exercise 1.1 of the chapter number 1, real numbers. So in the question number 1, it is given that use Euclid's division algorithm to find the SCF of. Okay. So starting with the very first question, as you can see here. So in the first part, we have to find the SCF of 135 and 225. So since 225 is greater than 135, so by using the or applying the division lemma to 225 and 135 to obtain, so we can write 225 as, or this equals to 135 into 1 plus 90. Then now since the remainder is 90, which is not equals to 0, we again apply this division lemma to 135 and 90. So we'll get 135 is equals to 90 into 1 plus 45. Now we consider the new or the divisor 90 and the new remainder 45, and apply the division lemma to obtain 90 is equals to 2 into 45 plus 0. So now here the remainder is 0, so the process stops. So therefore the 45 is the SCF of 135 and 225. Now then we have the second number 196 and 382. So just following the same process. So where the first step is 38220 is equal to 196 into 195 plus 0. As we can see in the very first step, we getting the remainder as a 0, so it means 196 is the SCF. Now in the third part, 867 and 255. Now since 867 is greater than 255, so again using the same process, so we can write here the first step. 867 is equal to 255 into 3 plus 102. So since the remainder is not equal to 0, so again we'll write 255 is equal to 102 into 2 plus 51. Now again the remainder is not 0, so again we can write here that 102 is equal to 51 into 2 plus 0. Now since the remainder is 0, so therefore 51 is the SCF. Now in the question number 2, show that any positive or integers is of the form 6q plus 1 or 6q plus 3 or 6q plus 5, where q is some integer. Now for this year, that is the year 2020 and 21, this is not in the syllabus, but still we have to do this. Okay, yes. So at least we should have an idea. Okay, so the students, those who are appearing for the board exam this year, that is 2020 and 21, okay, they can easily left such questions because this is among the deleted portion. Now, so how to show this? So let a be any positive integers and b is equals to 6. Then by the Euclid's algorithm, a is equals to 6q plus r for some integer where q is greater than or equals to 0 and r is equals to 0, 1, 2, 3, 4, 5. Right, because here the r is greater than or equals to 0 but less than 6. So therefore if a is equals to 6q or 6q plus 1 or 6q plus 2 or 6q plus 3 or 6q plus 4 or 6q plus 5 also. So 6q plus 1 is equals to 2 into 3q plus 1. So that is 2k plus 1 where k is a positive integer. So looking here, we are just trying to take 2 as a common. So then in the second part, if you say see here 6q plus 3. So 6q plus 3 again it is an again odd. 6q plus 5 is again odd. So we can clearly see that 6q plus 1, 6q plus 3, 6q plus 5 are of the form 2k plus 1, which means these are the odd form. So therefore 6q plus 1, 6q plus 3, 6q plus 3 are not exactly divided by 2. Okay, now then moving towards the next question number 3. In the question number 3, it is given that an army contingent of 616 members is to march behind an army band of 32 members in a parade. The two groups are to march in the same number of columns. So what is the maximum number of columns in which they can march? So SCF of 616 and 32 we have to find. So by using the Euclid's algorithm, we can find that is 612 is equals to 32 into 19 plus 8 and 32 is equals to 8 into 4 plus 0. So SCF of this is 8. Therefore they can march in the 8 columns. In the question number 4, use Euclid's division lemma to show that the square of any positive integer is either of the form 3m or 3m plus 1 for some integer m. Now, if you move towards just towards the solution, then looking at the solution, so what we are getting here. Okay, yes. So we can say let a be the any positive integer and b is equals to 3. So using Euclid's division lemma, we have a is equals to 3q plus r. It means that r equals to 0, 1, 2. So q is greater than or equals to 0 and r is greater than or equals to 0 but less than 3. So a is equals to 3q or aq is equals to 3q plus or aq is equals to 3q plus 2 because we are putting r is equals to 0, 1 and 2. So a square means 3q square or 3q plus 1 whole square or 3q plus 2 whole square. So this will become 3q whole square, 9q plus 6q plus 1, 9q square plus 12q plus 4. So here we can write it as 3 into 3q square, or this can be written as taking 3 as a common, 3 into 3q square plus 2q plus 1, or 3 into 3q square plus 4q plus 1 plus 1. Okay, so now, so we have 3k1 or 3k2 plus 1 or 3k3 plus 1. Now where k1, k2 and k3 are some positive integers, so hence it can be said the square of any positive integers is either of the form 3m or 3m plus 1. Now moving towards the question number 5. Use Euclid's division lemma to show that cube of any positive integer is of the form 9m, 9m plus 1 or 9m plus 8. Now let a be any positive integer and b is equal to 3. Use the Euclid's division lemma, a is equal to 3q plus r, where q is greater than equal to 0 or r is greater than equal to 0 less than 3. Therefore a is equal to 3q or 3q plus 1 or 3q plus 2. Therefore every number can be represented as these three forms. So case 1, when we have a is equal to 3q, so a cube can be written as 3q whole cube, that is equal to 27q cube, that can be written as 9 into 3q cube, that is 9m, where m is the integer such that m is equal to 3q cube. Then where a is equal to 3q plus 1, then again cubing on both sides, so result is a cube is equal to 27q cube plus 27q square plus 9q plus 1, that is 9, then bracket 3q cube plus 3q square plus q plus 1, that is 9m plus 1. So where m is an integer such that m is equal to 3q cube plus 3q square plus q. Okay, then we move towards the third part. So in the third part we can see here that it is a is equal to 3q plus 2. Now cubing on both sides, so we have a cube is equal to 3q plus 2 whole cube, which gives us a cube is equal to 27q cube plus 54q square plus 36q plus 8. Now a cube is equal to 9 within bracket 3q cube plus 6q square plus 4q plus 8. So we have a cube is equal to 9m plus 8. So where m is an integer such that m is equal to 3q cube plus 6q square plus 4q. So therefore cube of any positive integer of the form 9m, 9m plus 1 or 9m plus 8. So with this we come to the end of this exercise. So thank you very much.